Your power goes out at midnight, and instead of your smart home gracefully continuing to work like it's supposed to, you wake up to every light in the house blazing when the grid comes back online at 3 a.m., your door locks unresponsive, and your security sensors still trying to reconnect 20 minutes later. I'm Keiko Tanaka, and I spend most of my days figuring out how to make smart home tech actually invisible, the kind that works so well you forget it's there, especially when things go wrong. You're listening to Smart Home Setup Podcast. Quick heads up before we go any further, everything you're about to hear, all the research, the data, the script itself, that's been put together and verified by real human experts. The voice you're hearing, though, that's AI generated. Just wanted to be upfront about that. If you've been tuning in regularly, I'm really glad you're here. It means a lot that you keep coming back. And if this is your first episode, welcome. I think you're going to find this one useful. New episodes drop every Monday, Wednesday, and Friday, so you've got plenty to dig into. All right, let's jump right in. When the power fails, a well-designed smart home shouldn't become a haunted house of dead sensors and dark rooms. This checklist walks through the invisible infrastructure that keeps your automation running seamlessly during blackouts, from calculating UPS runtime for mesh networks to prioritizing which protocols recover fastest. You'll learn to size backup systems properly, understand fallback behaviors across Zigbee, Z-Wave, Thread, Matter, and Wi-Fi ecosystems, and configure automations that adapt gracefully when grid power vanishes. Now, let's talk about critical infrastructure, your hub and network priority. Your smart home's intelligence lives in its hubs and network infrastructure. When power fails, these devices determine whether automations continue or collapse entirely. First up, your router and modem need a dedicated UPS with minimum 2-hour runtime. Your Wi-Fi backbone serves multiple functions simultaneously. Cloud-connected devices need internet access. Mesh protocols use your network for remote control via smartphone apps. And hub firmware updates require connectivity during restoration. Calculate total wattage of router, modem, and any network switches, then size a UPS to deliver at least double that capacity for meaningful runtime. The APC Backups Pro 1500 VA handles most residential network setups reliably, though its fan activates audibly during battery operation, worth noting if your networking equipment lives in quiet spaces like bedroom closets. Check the link below to see the current price. Your primary hub for your dominant protocol should live on the same UPS as your network. If your home runs primarily Zigbee devices through a hub like the Philips Hue Bridge, that controller becomes your automation lifeline during outages. Check the link below to see the current price. Zigbee and Z-Wave mesh networks operate locally without internet. Automations continue executing as if-then logic stored on the hub itself. Thread networks similarly operate through border routers that maintain local mesh connectivity. Wi-Fi smart devices, conversely, often lose all automation capabilities without cloud access, even if your local network stays powered. Secondary hubs for mixed protocol homes require separate runtime calculation. Homes blending ecosystems need power planning for each protocol family. A Z-Wave hub managing door locks and sensors draws different wattage than a Matter over Thread border router controlling lighting. Understanding which devices need which bridges clarifies your backup power architecture before you size UPS systems. Here's something interesting. Smart switches and wired sensors maintain position memory, while battery sensors enter low power mode. Hardwired in-wall smart switches, whether they're Zigbee, Z-Wave, or Matter certified, typically remember their last state when power returns, reconnecting to mesh networks within 30 to 90 seconds. Battery-powered sensors like motion detectors, door contacts, and temperature monitors continue reporting to hubs during outages, but many enter power conservation modes that increase reporting latency from under 1 second to 5 to 15 seconds.
This delay affects security automations that depend on instant motion detection. Cloud-dependent automations fail regardless of local power backup. If your lighting scenes run through cloud services, most Wi-Fi bulbs, some poorly configured smart home platforms, local UPS units won't restore functionality during internet outages. Prioritize local automation logic over cloud-based triggers for critical functions like entryway lighting, security responses, and accessibility features. Mesh network recovery time varies by protocol density. A Zigbee network with 40-plus devices on a powered hub recovers in 2 to 4 minutes as nodes rediscover routes. Sparse networks with 5 to 8 devices reconnect in 15 to 45 seconds. Z-Wave networks typically recover faster due to more deliberate routing tables, while thread networks excel at rapid mesh reformation thanks to their self-healing architecture. Plan for this latency when testing automations after power restoration. Don't assume instant responsiveness. If you're using Matter to bridge thread to other protocols, you've introduced recovery dependencies. Matter over thread bridged to other protocols means power restoration triggers a cascade. Thread border router comes online, Matter fabric reestablishes, then cross-protocol bridges reconnect. This adds 30 to 90 seconds to full automation availability compared to single protocol systems. Matter 1.4's improved fabric recovery reduces this delay, but testing your specific device combinations reveals real-world timing. Moving on to device-level backup, what needs power and what doesn't? Not every smart device requires backup power. Strategic selection keeps costs reasonable while maintaining essential functions. Battery-powered sensors continue operating independently during outages. Zigbee motion sensors, Z-Wave door contacts, and thread temperature monitors run on coin cells or AA batteries for months. They'll keep reporting to hubs, assuming those hubs stay powered, but verify their fallback behavior. Some devices cache data locally when hub communication fails, others simply stop trying after 3 to 5 failed transmission attempts.
Smart locks with battery backup operate locally but lose remote access. Most Z-Wave and Thread smart locks maintain manual code entry and physical key operation during power failures. The lock mechanism itself runs on batteries, but remote unlocking via smartphone requires your hub and network to stay powered. If elder care or accessibility needs demand remote unlock capability during outages, dedicated UPS coverage for your network and lock hub becomes non-negotiable. Hardwired cameras lose all functionality without backup power. PoE security cameras, wired video doorbells, and DVR systems go completely dark unless connected to UPS or battery backup. Wireless cameras with local batteries continue recording but can't upload footage without powered network infrastructure. For subscription-free setups relying on local storage security systems, ensure both camera power and NVR or DVR receive backup coverage. Smart thermostats maintain schedules but can't control HVAC without system power. Even battery-equipped thermostats like Nest or Ecobee lose climate control when your furnace or air handler shuts down. The thermostat display stays active, but automations triggering temperature adjustments become meaningless. In freezing climates, this matters. Consider whether whole home battery systems make sense for maintaining heat during extended outages. Irrigation controllers on battery backup prevent missed watering windows. Smart sprinkler systems like Rakio or Orbit Beehive include backup batteries that preserve schedules during brief outages, but battery runtime typically maxes out at 24 hours. If you've configured complex zone logic with weather integration, longer outages erase queued schedules. Some controllers revert to manual bypass valves. Verify your system's fallback behavior before relying on it during vacation absences. Voice assistants require continuous power for wake word detection. Amazon Echo, Google Nest, and Apple HomePod devices contain no internal batteries, except HomePod Mini's brief handoff buffer.
Without power, voice control vanishes entirely. If accessibility needs make voice commands essential, small UPS units for smart speakers cost less than whole home solutions, a practical middle ground for design-conscious spaces where disguised smart speakers already blend into furniture. Next, let's get into automation logic and fallback configuration. The most elegant power outage preparation happens in software, automations that adapt to degraded conditions without human intervention.
Configure power-restored automations to re-establish baseline states. When grid power returns, your smart home wakes up chaotically. Some devices reconnect instantly, others lag 3 to 5 minutes, creating inconsistent automation states. Build a dedicated restoration routine. If hub connectivity restored and time is greater than 10 minutes since last power event, then set all lights to off, lock exterior doors, resume normal schedule. This prevents the common scenario where every light in the house turns on at 3 a.m. when power comes back. Priority routing for critical automations during low battery UPS states helps too. Advanced UPS models with smart outlets send low battery warnings to hubs via USB or network connections. Configure conditional logic. If UPS battery is less than 20%, then disable non-essential automations, suspend polling for energy monitoring devices, reduce lighting scene complexity to binary on-off. This extends runtime for security and accessibility functions by shedding luxury automations. Fall back to local schedules when cloud services time out. Many smart home platforms let you duplicate cloud-based automations as local timers. For morning routines, create parallel automation paths. If sunrise time from Weather API available, then trigger wake-up scene. Else, if 6:30 a.m. local time, then trigger wake-up scene. The first path offers seasonal accuracy, the second ensures functionality during internet outages. Motion-activated lighting with occupancy memory prevents dark hallways. Standard motion triggers fail during sensor battery conservation modes that increase latency. Add redundancy. If bathroom motion detected or bathroom door opened within the last 30 seconds or bathroom occupied for greater than 1 minute from previous trigger, then turn on lights for 10 minutes. This multi-input logic compensates for slow reporting sensors during outages. Security system arming delays should account for hub recovery time. Don't arm your security system immediately after power restoration. Give mesh networks time to stabilize. Configure this. If power outage detected, then delay security arming by 5 minutes after power restoration. Send notification to confirm manual override. This prevents false alarms from sensors still rejoining the network. Now, UPS sizing and runtime calculation. Properly sized battery backup requires more nuance than bigger is better. You're balancing runtime, budget, and the physical reality of where equipment lives in your home.
Calculate wattage draw for always-on devices, not peak ratings. Your router's power supply might claim 60 watts, but actual draw during operation typically measures 12 to 18 watts. Use a smart plug with energy monitoring to measure real consumption over 24 hours before sizing UPS capacity. Mesh network hubs draw 2 to 8 watts, security cameras 4 to 12 watts each, NAS devices 15 to 45 watts depending on drive count. Total these measured values, then apply the runtime formula. UPS watt-hours divided by total device watts equals runtime in hours. Account for battery aging and temperature derating. UPS manufacturers rate batteries at 77 degrees Fahrenheit under ideal conditions. If your network equipment lives in a garage where summer temps hit 95 degrees or a basement hovering at 55 degrees, expect 20 to 40% runtime reduction. Similarly, batteries lose 15 to 20% capacity per year. Detailed runtime calculations that factor environmental conditions prevent disappointing real-world performance. Match UPS form factor to installation location.
Rack-mount UPS units make sense for equipment closets with structured networking, but tower models integrate more naturally into living spaces. The spatial consideration matters when you're trying to hide smart home infrastructure without blocking wireless signals. UPS units generate RF noise that can interfere with Zigbee at 2.4 GHz if placed directly adjacent to hubs. Maintain 18 to 24 inches of separation. Runtime targets differ by outage duration patterns in your region. If your local utility typically resolves outages in 15 to 45 minutes, a UPS providing 2 hours of hub and network runtime offers comfortable margin. Areas experiencing 4 to 8 hour outages during storms need different math, either substantially larger UPS capacity or whole home battery integration becomes more cost-effective than scaling up individual UPS units. Smart UPS models enable remote shutdown and startup automations. Network-connected UPS systems from APC, CyberPower, and Eaton expose battery state via SNMP, allowing Home Assistant energy automations to react intelligently. Configure this. If UPS runtime remaining is less than 10 minutes, then shut down NAS gracefully, send critical alert, disable HVAC automations. This prevents data corruption and extends battery life for truly essential devices. Here's your final check before you go. For pre-outage preparation, make sure all hubs and routers are connected to appropriately sized UPS units. Measure actual wattage draw of powered devices, not nameplate ratings. Runtime calculations should account for battery age and ambient temperature. Test your UPS self-test function within the last 3 months. Verify battery replacement date. Most UPS batteries last 3 to 5 years.
For protocol-specific verification, confirm Zigbee and Z-Wave hubs have local automation logic, not cloud-dependent. Thread border routers should remain powered alongside Matter-certified devices. Document Wi-Fi device cloud dependencies. These will fail during internet outages. Battery-powered sensors should show greater than 50% charge levels in their respective apps. For automation logic, configure power restored routines to re-establish baseline states. Low battery UPS warnings should trigger automation load shedding. Critical security and accessibility functions need local fallback schedules. Motion lighting should include redundant triggers for sensor latency during outages. For physical installation, place UPS units 18+ inches from Zigbee and Thread hubs to avoid RF interference. Use battery backup surge protectors, not just surge strips without battery. Concealed hub locations still need to allow adequate UPS cooling airflow. Let's go through some frequently asked questions. How long do Zigbee and Z-Wave mesh networks take to recover after power is restored? Zigbee and Z-Wave mesh networks typically take 2 to 5 minutes to fully re-establish routing tables after power restoration, with device count and network density affecting recovery time. Networks with 40+ devices can take up to 8 minutes, while smaller 10-device networks often reconnect in under 90 seconds. Individual battery-powered sensors may enter power conservation modes that increase response latency by 5 to 15 seconds during the recovery window. Should I put my smart bulbs on UPS backup or just the hub? Put your hub on UPS backup, not individual smart bulbs. Zigbee, Z-Wave, and Thread bulbs lose power when their fixture circuit dies regardless of hub status, and maintaining hub power ensures battery-operated sensors and switches continue executing local automations during outages. Keeping smart bulbs powered during whole home blackouts serves no functional purpose unless you're also backing up the specific circuits they're wired to via whole home battery or generator systems. Do Matter 1.4 devices reconnect faster than older protocols after power outages? Matter 1.4 devices reconnect comparably to mature Zigbee and Z-Wave implementations, typically 60 to 120 seconds for full mesh reformation. The primary advantage is improved cross-protocol bridge recovery when Matter unifies Thread, Zigbee, and Wi-Fi devices through a single fabric, though real-world performance depends heavily on your specific border router quality and whether you're using Thread or Wi-Fi as Matter's underlying transport layer.
The most successful smart home power outage preparation feels invisible until it's needed, like proper insulation or well-placed lighting. The infrastructure simply works without announcing itself. A well-sized UPS tucked behind your networking equipment, automations that gracefully degrade functionality rather than failing completely, and protocol choices that prioritize local operation over cloud dependence all contribute to a home that continues feeling smart even when the grid forgets its job. The checklist above isn't about preparing for disaster. It's about maintaining the seamless daily rhythms that make technology worth integrating in the first place. Test your backup systems twice yearly, once in spring before storm season, once in fall before winter weather. Simulate power failures by tripping the breaker. Observe which automations adapt and which stumble, then refine your logic accordingly. Your smart home should serve you most reliably when conditions are least reliable.
Thanks for listening to this episode of Smart Home Setup Podcast. New episodes come out every Monday, Wednesday, and Friday, so you've always got something fresh to check out. If you found this helpful, I'd really appreciate it if you left a 5-star rating and a quick review. It actually makes a difference in helping other people discover the show when they're searching for smart home advice. And if you haven't already, hit subscribe or follow so you get notified the second new episodes go live. I'll catch you on the next one.